$28. Change up that logo, change the design a little bit. Call it a You're sitting that like Apple and like other I'm not looking for it. There are two different versions of
All right, everyone. For those who just came into the class, make sure you have one of the worksheets that's put on the back of the table. Make sure you grab one of the worksheets. All right, let's get the class started. So how is the exam one last Friday? Any thoughts? No comments? Glad you survived. Was it okay-ish? Okay. I see how it is. So today we'll be talking about the virtual timers. Besides that, we also talk about the project ideation and project team forming, which will be happening this Friday. And the project ideation slides will be due on the night before, so that everyone will have some kind of understanding of what each other's thoughts are. So that helps you kind of find like the close ideas or the ideas you found interesting, so that you can form the team hopefully more effectively during Friday. Let's get into the class. So first thing first, we have the homework 4 posted. We're giving everyone one extra day so that it's going to be due on Saturday, the 15th, instead of the 14th. We're aware that this week might be a little bit overwhelming, and we hope that this homework deadline does not mess with anyone's 14th night. So hopefully that's a good news for you guys. Anyway. We have the exam 1 pretty much graded. We will be releasing it tonight, hopefully. This is like a general distribution of the score. Where do I start? It looks like a left-held normal distribution, which might be expected. The mean is around like low 70s. Just to give you some additional, like some initial thoughts. And the standard deviation is around, I think, 16, give or take. So majority of the class did it between, I believe, 60 and 90. Do you guys run into any questions regarding this distribution, or any additional questions you want to ask at this moment? Yes.
What does the curve look like?
What's the curve look like? That's a great question. You notice that we didn't. So we didn't. Well, I didn't put the mains and median here just yet because we are still kind of massaging the scores. Stats is a very peculiar subject. We'll let you know. We're gonna have a discussion today, and yes. Any other things? Yes.
Was distribution higher, lower, kind of the same as like historically? What's been the case for first term?
Yes, I think historically the terms that I'm aware of, it's usually around like 70 something, lower, like below 75 as the midterm average. So that is the target we're trying to hit as well. Any other questions? Yes.
Do you have any idea of what like the grade thresholds are going to be for the semester?
The grade what?
Like the grade thresholds for the semester are going to be?
It's going to be depends a little bit on the exam too as well. But I think generally the average score with this class, if you guys all did great, should be like a B+. So I wouldn't worry too much. I hope. I mean, you also don't worry too much. Any other questions? I think the final project is, as you will learn, it's like a big chunk of the score. So Any other questions? Everyone is good? Good with the, so we will be, after we release the score, we will also release the solutions, and we will keep the regraded options open for an additional week. So from today, probably we're gonna open it until next Wednesday. If you see anything in your solutions that you believe that it's maybe have some partial credits, or we made some small mistakes when grading your scores, please just submit one on the grade scope, and then we will have it regraded. All right, that's everything. Any other additional thoughts about the exam 1? Okay, cool. Let's get that out of the way. So we're gonna officially entering the kind of the start of the final project. We're gonna have you. So the first thing first, this Friday we were gonna have the team formation pizza event at the GG Brown building. 1571 from 4:30 to 6:30 p.m. You could leave early, but just trying to be there at the beginning of the event, and also make sure you leave after you find your teammates and everything. We're gonna enforce the groups to be a group size of 4. Because this time we have a historically high enrollment of the class members. In order for the teaching team to have enough bandwidth with each team on the final projects, we're gonna have to leave the we're gonna have to cap the overall team number. So we're gonna try to enforce you guys. We're gonna enforce the team number to be 4 people per team, and. One of the things that's going to be due before the team formation event is this ideation slides. It's pretty much 3 slides. You can do it on Google Slides, or if you prefer a PowerPoint, you can also do that, and then upload it to the shared Google Drive with like a PDF file or something. So basically, it's going to be looking something like this, and you should treat it as a brainstorm sessions. We're not gonna ask for a lot of details, but basically, let me show you one of the templates. Something like one idealization slides would be something like this. You have some sort of drawings to give an idea of how or what's the device, or how things could look like, and which environment is gonna be used in, and then you have some text in the slides, less than 100 words-ish, and then just describe what you want this device to do and what's the general idea of this, the idea that you're trying to propose. Make sure you put a star at the top ideas of yours. Each of you are gonna have 3, and in the end, let me show you. We're gonna have this folder. Where's the folder? Submission folder. Yes. We have this submission folder. I think it's already on the class website. So, someone is already okay. Good for you. Basically, everyone will have access to this, and then you can kind of browse through other folks' ideas. Try to do that after you submit yours, and then find the ones that you also find interesting and fun projects, so that in the team formation events, we can kind of talk to each other based on the components you kind of want to use, or the idea in general. Yes?
If we already have someone that we want to partner with, then we're gonna partner together. Can we do this part together?
For this part, we were still gonna ask you to do it individually. Yeah, chances are each of you gonna have more than one ideas, right? Also, you could have a. Okay, how do we do this? Okay, let's have one shared slides at most. So at least you have to come up with 2 individual ones. That's different from any of the teammates you're already kind of talking to or formed. Yeah, also on that topic, even if you have a teammate or a couple teammates that you have in mind, still try to come to the event. The only ways to get accepted from this is that the 4 of you submitted a project proposal. That's kind of in a much more detailed way, rather than the 3 ideation slides. So considering the amount of work that required, I recommend you to just come to the event and have some pizza and some drinks, rather than spend 3-4 hours working together on that. And you're gonna still work on that later anyway. Yeah. Any other questions on these? I can also show you. We also included some previous examples. Those are pretty good ones. For example, this is how a pretty decent slides would look like. I believe for this one, they're trying to do a alarm thing that runs around when it's doing the alarm, so that you have to actually get out of the bed in order to catch it. So you have to actually get up in order to kill your alarm. Pretty decent. I think this was probably for people of 3. So if you want to do something similar to this, you probably want to add a little bit more. Maybe the clock also jumps or something. This one is fancy figures, right? But the idea is pretty concrete. Basically, they're trying to build this tech lab thing that have a few vehicle kind of thing that are moving around in this area, and then they communicate each other, or they trying to avoid the pedestrians or objects on the way. so to speak. This one is a phone charger that, now at this stage, you can think a little bit bold or a little bit out of the box. Yes, because chances are these things are, some of them are not going to be, built in the end, or at least not going to be as you envision it to be, which is very common in like product design. Yeah, but at this stage, feel free to think about bold and then think out of the box. This one is like a moving phone chargers. If it detects your phone's below a certain battery level, it kind of come to you and then piggyback the iPhone or Android phone, whichever one you use, and then start to charging. And this one is more on like the accessibility side. Basically, you have this glove thing that you build, and then that can do the like inputs for the VR environment, for the sign language, etc. So just give you some examples of how like some of the previous pretty decent ideations slides. Any questions on this one? Okay, perfect. So yes.
So should we like follow one of these ideas in the final project? I mean, combine. So we choose like from 12 ideas and then combine 4 of them together.
I think generally you will be, yeah. So the team of you will, you don't have to pick one of these ideations in the end. These are mainly kind of like a showcase of your creativity and your self. Show your characteristics. So if you have like great ideation slides, chances are you're gonna have cool people talking to you during the team formation. Not saying like other people are not cool, but like cool people with extra efforts put into it. So yeah. And in the end, the team will be deciding and also talking with us. We will decide which projects are actually like feasible and within the components we're able to reach, etc. But yeah, but at the ideation, feel free to think bold and then go beyond the budget or anything. That might be. Any other questions? Let me check. Also, we also included like a more detailed handouts in that document. Will be linked to this as well. So give you some overview of how this project is going to work, and how the grade is going to be distributed roughly, based on how well the idea is, how many components you guys have, and how difficult these components are to be integrated, as well as presentations and demos in the end. All of these are on the class website in the slides handout in this one. Any questions around this? I think today we probably gonna have some extra time in the lecture. So if you want to, because the virtual timer is not a lot of content, so you could just stay here and work on this if you want. Any other questions regarding ideation slides or regarding the team forming or general anything regarding the Friday event? Okay, seems like everyone is ready. Nice. All right, so let's go into the lecture content today. Basically, we're gonna do the little bit timer review because that's pre-exam 1. Just want to make sure that everyone still kind of remember that. And then we're gonna mainly talk about the virtual timer today. I think we'll probably save the communication buses for the next lecture so that you guys have more time working on other stuff. But basically, yeah, the timer that we talked before, this is like a general structure of how it works. We have like an actual clock, physical clock with usually crystals, etc. And then coming with a clock cycle. And then we go through like a prescaler to usually scale down the clock to like a more suitable range for most of your, or for this batch of the registers or devices. And then we have like a time counter that basically doing the count and then use that as the value to see if any interrupts or any periodic events that occurs that needs to be happened. And for the periodic events that usually stored in this ARR register, it's basically the auto reload register. You put a number in there, it will just do the counting, and then whenever it counts at that number, it will trigger a event and then reload itself to do it again. And whenever that happens, that could trigger a interrupt, like an ISR interrupt, and then let the system to depart from whatever it was currently doing to another thing. And on top of this, we also have a CCR, or compare and capture registers. Basically, they're used to doing a lot of times like some batch controls or batching in the instructions. This would be like for the input capture. Usually in the input mode, basically you have like some GPIO values or some values from peripherals coming into this, and then you will compare it. It will capture that, and then basically store that value when that happens. Basically, take that and then take the value from the current timer and save that time event inside of this register. And if that time, and then that time value will be then used for some other things. For example, some interrupts or other events or other flag updates. And we also have the CCR in the compare mode, which usually is used in kind of like the output mode. One of the examples what we gave before was the PWM, which we'll also go briefly in the next slides. Basically, similar to before, we have a value stored in the CCR, and then it constantly check with the timer counter, and whenever it's equals or something, and then it triggers a ISR, like an interrupting event happening. In this case, for the example of like a PWM, basically that determines one, the output should be high, one it should be low. So that generates a nice pause modulation, like a PWM signal. And just to go a little bit in details on that, this is also a review from the previous lecture. Basically, we have different modes of the PWM. This is like a low true mode, meaning, let me just put everything. Whenever the value of the counter is below a CCR values, the value stored in CCR. CCR is the capture compare register that we just mentioned. And then it will output a high signal. And then whenever the counter value goes beyond the CCR register, it will basically give like a low signal output. And these are like the formulas that we use to calculate the duty cycle as well as the period based on these values. Any questions from this? This is from previous lecture, but I suspect a lot of the content went through because of the midterm. Any questions around this? Yes?
Is the clock period there after prescaling?
That's a good question. Yes, the clock period is after the prescaler. All right. So we also have like the high true, works similarly. It's just that it's the value that's above the CCR, the capture compare registers value. The output becomes high, and otherwise it becomes low. And you also, by the way, you also see this RCR values. This is basically the repetition counter register that gives an additional control where you can tell among like these periods, you can also give them one extra number. Say if it's give 1 or 2, then it's every 1 or 2 cycle, it does one of this up and downs. It'll just give you like one additional control on how much time you want to wait or what's the form of the PWM signal looks like. yeah, this is just another example here. The main part here is that just show you that how usually we change the duty cycle. So previously we used the duty cycle as 3, like the CCR as 3 for both high chew and low chew. That gives slightly different result on the duty cycle, 4/7 or 3/7. And then in order to change that on the go, you will be basically change the CCR values. And then that gives you an update on the duty cycle. These things are, you can typically update these in the program or while you are executing in the hardware into different phases. And usually the periods of the PWM signal is set at once at the initialized stage. And then you usually try to keep that the same across the program execution, just to have the system to be more stable. And we also have the the come down, come up, and come down counter here. So basically, in this case, if we still have like a high chew version, then everything above this will be similarly as before. But the thing that's changed is the periods will be changed. I think with the calculation for the periods will be changed here. Besides that, I think these things are pretty similar as before. Just make sure you know how many cycles are on top of this value, how many of them are on the bottom, so that you can have a duty cycle calculated. Yeah, again, changing the duty cycle will be a change in the CCR value, the value stored in the CCR register. This part is good? Okay, perfect. And yeah, this is like another view from like a top, like more abstract views. Basically, once we have those counters and prescalers and counters set up, they could have each link. One of the counters or one of these timers can be linked to multiple CCR registers, so that one timer can essentially control multiple of these interrupts or events based on that. And today's lecture, we're also going to talk a little bit, even on top of this, we can have like even virtual timers, so that a single timer can, in this case, single timers can basically generate 4 different PWM signals running on the same timer. And today's lecture, we will introduce another layer, which is like virtual timers, and then you're able to drive even more stuff. But for that part, it's usually used for something like slower and doesn't require as precise execution as opposed to these things, usually in like milliseconds or even faster, if you want to have like a very precise control. Any questions on this? Okay, perfect. So then we're going to go to the worksheet of the day. And basically what we're trying to do here is, given this clock and then the counter, it's basically everything we talked before, and then make a timer setup that will generate a PWM output of a duty cycle of 10% and a period of 10 milliseconds. And anyone don't have the worksheet? Please work with your neighbors as well, and talk to each other, and yeah. Cool. Okay.
Our TCR is clock, cycle of 10%, and 3 is 10.
Oh, also, you can probably imagine we will have like more than one correct answers on this.
No, just spreads like 4. Yeah, that No, I think it's just, I don't think that is secure. Anyway, look at this equation. Period is equal to ARR times 2 times clock period. And clock period is just 60 megahertz. I'm going to do 6025 or 125. Alright, 8. Yeah, okay, I was basically right. Off by a couple words. Wait, you said ARR is 8,000? Oh, okay, well, by one order. No, it's just a unit list. Right, 16 megahertz.
Yeah, so 1 over 60 times 10 to the 6.
What? 6.5.
6.25 to minus 3. And then 0.01 divided by that.
0.5. Wait, you said 80. You said 80,000. Okay, so then, you want that to be true, it'll have to be. That's oh, wait, that? Yeah. Yeah, it's 72,000. Wait, there is 80,000.
My brain is constantly ITA.
For sure this equation is right? Yeah, yeah. It's a very good question. What's PSC? PSC. Oh, yeah. That's it's the three scalar thing. Yeah, you basically that's way, yeah. No, that's not really true. Yeah, ARR, RCC. What's a PWM?
Oh, yeah, it's
So those numbers are just like show. You don't have to choose the counter to count up to 6 and then come down from 6. All the values are open for you to set. Like the scalar, pre-scalar, the AR counters value, the CCR value of the cutoff. Any of these, if you want to be fancy, you can also use the RCR value that sets how many multiple periods of the PWM signal one event triggered. So everything is for the setting.
What is oh wait, you're nice, so I made sure to do that.
We started
Colin found a formula, but I don't remember it yet. Oh. Why did you have to put, oh, the plus one? So it's 10 milliseconds over 62.5 nanoseconds minus. I feel like it would be I'm gonna guess 199,000. Oh yeah, I guess that was. Oh, but then you can do either. Then it'll be like
might as well since it's supposed to be on the board.
But shouldn't the frequency of the clock be?
It's, I think we're your guess is still like he seems confused when I'm solving this and then
Where any it's got to be less than 60. I'm gonna go with in this case, one power of every number. Yeah. Oh, you can solve for FQs.
I'm not sure how to
Hey,
All right. All right. How is everyone doing? How are we doing? All right. Who wants to share some clock configurations? Any volunteers? There are going to be a lot of solutions here. So, but any volunteers want to share their configuration? And then someone with the calculator can help us decide if the answer is actually correct. Anyone? Nobody? I thought there was a lot of discussion going there. Yes?
So I use the prescaler of 500.
Prescaler 500. So what's the scaled clock going to be? The clock?
It was 0.00, for the period of 0.005.
Okay. What's the frequency that's going to be scaled down to? Is it 500? Because remember, when you use the prescaler, that's a well, I wouldn't say string. You can choose any values you want. Remember from the previous slides, basically when you chose the prescalers, okay, it's actually not here. Sorry. When you chose the prescalers, the system will add 1 to that value and use that as the factor to be divided by. So say if you have 500 for that number, the system will divide it, the 16 megahertz by 501, and then give you like a clock for the remaining system. The reason that they put an additional 1 to that because it's a divider. So previously, a lot of the not super matured programmers, they sometimes just put 0 there and then cause the system failures. So they just make sure they just basically encoded 1 there, and then whatever number you put there, they will add 1 to it for calculating the scaled clock. But we're on good track. So say if you have the clock scalar prescaler to be 499, and then we have the 500, and then what's that value give you? What's the current frequency? I saw you did the calculation somewhere. What? Okay, 32 kilohertz. And then what's the value for the CCR, the compare and, sorry, what's the value for the AR, like the auto reload register value you chose?
I tried to make my auto reload 10 and then my CCR 9, just to make the numbers easy.
Okay, so to be the 9, and because we're doing like a up and down counter, what's that value gives us? So 20 CCR. If you have that as 10 and then cut off at 9, I think that will give you 5% or closer to 5% compared to 10%, right? So if you have, say, the value AR value to be 10, then basically that to be 9, the cutoff is basically 1 above the entire cutoff, like the CCR value. By the way, let me before I answer that, we do run into people a little bit confused about this, like asymmetric or symmetric thing. You might notice that the number sometimes doesn't add up. You might have like say 1 pivot out above the CCR or 2 pivot above the CCR. In practice, usually what's like a typical ways to get around that is we will basically choose like a larger CCR value, sorry, the larger ARR value. So let's say if you have like 100 and then everything above 10, it's considered as high. Then whether it's 10 cycles above that threshold or 11 cycles above that threshold become much less an issue. If you say chose the ARR value to be 1,000, then if it's like 100 cycles above or 101 cycles above, then it became much less of a issue. But to be absolutely accurate, basically it does the integer divide. So whatever the number comes from there, that's typically be considered as what you're going to have for above the threshold. Was that the same question you were asking, or okay, never mind. Any other questions before we move on? Keep like calculating together. Okay, so anyone else want to share their answers? All right, let me share my. Well, it's not really mine, but from previous folks. So basically, this is like the end signals that we're trying to get, and that was the formula will be used for the prescaler. Like, what's the output from the prescaler? Make sure you add 1 to that every time. And the 16 megahertz in this case is the clocking, like the clock that's generated by, say, Crystal or whatever source that was built with the system. And yeah, so for this one, we have basically a prescaler of 15. So after that, we have a clock of like a scaled timer clock as a 1 megahertz. And then we set the ARR, the auto reload register, to be 5,000. And then, the CCR value, the cutoff, is the 4,500. So basically, on each of the slope, we have we have like a 500 above and 500 down. So in the end, I believe the math setup, I did check that. So anything, a lot of solutions can be have for these combinations as long as you make the end the correct signal you're trying to have. This will be very common for you guys when doing like final projects or like real time, like the real world solutions, where chances are you're going to have a lot of correct choices for the signal you have. And yeah, any questions on this worksheet? Yeah.
So how do you like decide what to make the clock period iteration?
That's a great question. How do we decide? That's a lot of times you will say you hear that normally people do this and do that. These are kind of considered as insights. So those are the experience that you basically build along the way when you deal with different types of devices or peripherals. But generally speaking, these values are basically being designed so that you can have some design trade-offs. For example, for the prescalers, if you want something to be like high frequency, you would choose like a lower value for that. For example, say for like 1 to 10 or 1 to 20-ish, and then those will give you much more control over the signals that you're trying to send if it's required for higher frequency. For example, if you do like LED dimming, so you're not really turning it off, but you're basically turning it on and off so fast that to human eyes, that's practically a low. So or like motor controls. So for those ones, it also depends on how fast. But those things are usually requires like higher frequency signals. So you use like a smaller, like in the low 20 or like 10 to 20-ish. And then if you want to have, say, like higher resolution PWMs, that's where you're gonna set the ARR value to be high. For the previous question, because we didn't specify which components it's been connected to or which type of interaction it's been used for. So basically a lot of values can be accepted, but I can give you an example for the higher resolution PWM signals. For example, if you want to do like some audio output, for example, then you would like to have much more control over the number of up and lows of the overall like resolution of the PWM signal. And sorry, let me just finish the remaining. And for these ones, you can have a much larger ARR value. The real up threshold is based on how many registered bits that's encoded within the ARR. I think our system use 32-bit, that's a pretty large number. Some of the systems out there use like 16-bit, so that's like the hard cutoff for this type of, depends on how many resolutions you want. And for the CCR, that's basically, just decide, it depends on how precise you want the controls to be. You can always do like 10%-ish, use a number, or you do very, very precise, out of, I don't know, 100,000, like say 5,000 ARR value, and we want 2,356 to be the CCR. So that gives you a very precise control over, say, if you do like some server turning or like some robotics control, you just want it to be much more precise. And for the RCR value, the repeated registers, I think oftentimes we don't use it that much. I think they usually really be used when you're trying to have less interrupted for any particular peripherals or devices to be used. You might run into that for your final project, but yeah. Does that answer? But basically, I think for the prescalers, it's usually between like 10-ish to 100-ish. That should be suitable for most of the devices. Obviously, you will have to check what's the device spec set. Sometimes the device specs will give you a clock cycle that it runs on, or a range. You should make sure that clock goes into that range. So yeah. Yeah, so yeah, that's the question?
So for active high or mode 2, didn't we say that it's active if it's higher or equal? And in this case, if we choose CCR and ARR to be the same number, we get a duty cycle of 0. Is that right?
If we have the ARR and the CCR value to be the same.
Yeah, shouldn't it be active on just the highest number, but in the equation we would get 0?
Yes, that should be 0. Yeah, I mean, that's a very good point, but usually we would treat it as a 0. If you think about this, you have 5,000. 1 out of 5,000 is pretty close to 0. Don't overthink on each one individual cycles, so to speak. It's, yeah. Any other questions? Yeah.
On the slides, I noticed there were 2 different formulas. I think one's on like slide 8 and one on slide 9.
8 and 9. This one? And this one?
There's one that's like CCR over ARR plus 1 format set value, and the other one that we said is format is CCR over ARR.
Oh, yeah, so it's always AR plus 1. Here, you mean here? You mean this value?
Yes, but there's one on the slide below it. There's a couple.
This one?
No, go to the next one.
Oh, where? This one? Oh, up and down. Yeah, because it's up down. That's all. Yeah.
One of them has AR plus 1 on the denominator, whereas that's just CCR. Yeah, the difference right there.
Yeah, because one of them is high true or low true. The other one, one of them is the counter that counting up or counting down. That's and then directly go back to 0. The other mode is the counter counts up and then come down. That's why there is a slight difference in this formula. And in the worksheet example we have, it's count up and down. Good. Okay. Any other questions? Okay. Perfect. And let me just do another quick brainstorm with your neighbors. Basically, say if we have like an input clock of 100 megahertz, what's the maximum timeout period we can have for each of the bit we assigned to the timer? Okay. Talk to your neighbor and then, yeah, let's work it out. This you can think about like how many cycles in total we could have a sleep and then back on and then sleep, etc. You can basically think of it as this entire bit is dedicated to be just waiting and how many times that can have the whole system waited for. Yeah.
That would be like,
Okay, how much with a 16-bit timer? How long we're able to have the system wait for us with that one timer? If we counted the entire timer to be, wait or whatever instruction. Any answers? Anyone calculated based on 100 megahertz clock, which is pretty fast? Any results from the calculator? Yes.
For 16, it's like 1.3 milliseconds.
Are you using like one of the clock cycle or the entire 16-bit as the counted as a timeout?
So we thought if you count up and then count down, that could be the maximum timeout.
I see. Okay, so for this one, this 16-bit here was referring to the, let's see, say, okay, I think it's not in the slides. But basically, you can think of it, you have a 100 hertz, megahertz signal coming in, right? And we have a timer here that all it does, it's maxing out the timeout period, or max it out how much it's able to make each time cycle to be, so to speak, with all the 16-bit used. Exactly, you can use that to build like a gigantic prescaler, so to speak. So sorry for the confusing. Anyone had that used as a prescaler? Yeah. No? Okay. Anyone? Okay, basically for this one, it's going to be 0.6 milliseconds, give or take. And how about 32-bit? Now the calculation formula got confirmed. Anyone wants to share the result on the 32-bit timer? How long maximum we can, yes?
About 43 seconds.
About 43 seconds, that is correct. How about 64-bit timer? Anyone done the calculation yet? Anyone? Okay, so it's about, I think, 5,800 something years. So, not typically wouldn't put like 16-bit into a timer for a reason, because that's kind of overkill for most of the interactions that human needs at this point. Anyway, yeah. Next, we're gonna talk about like the virtual timer on top of the, basically this was the anatomy of the timer systems. Previously, we talked about like the hardware side, and then with prescalers, with a bunch of registers that give you extra controls. And on top of that, we also have the operating systems. So basically, everything below this is being handled by this subsystem device drivers. So when it goes to this operation system, everything will kind of look the same to them, except for the characteristics of this timer. So it doesn't matter whether the clock was driven by a crystal or different materials, but at that level, from systems perspective, it basically looks the same. And then at that level, it will be able to do some abstractions and the virtualizations for these input timer from the hardware, and then use that to share with different devices or different peripherals. And the reason is, well, if you think about it, we have just too many things ongoing at the same time, right? If we have one hardware timers for each of these setup, or even with all the registers we have, it's still going to be a very hard to distribute, considering how complicated nowadays computation is going to be. So the system, at the system level, we will probably do some, if you imagine, we can probably do something within like the software to make it kind of shared by a lot of events. So for example, a lot of the events that run one set of one timer, but just has different times to be triggering them. And let's quickly brainstorm, like how would you design the system? Say if we have a bunch of interrupt events, or bunch of events in general that needs to happen at different time. How would you say use like one timers to just have them sorted out and executed correctly? Let's do another quick discussion with your neighbors, and then let's get back to it. Okay, any ideas how we're going to do this? What are the possible solutions we have? Any software solutions? Okay. Yeah.
A variable you just keep adding to every clock cycle.
Keep adding what, sorry?
Like a variable you just keep adding to every clock cycle.
You just keep adding events to the...
Yeah, like a counter. And then
and you make sure they got updated every clock cycle, so to speak. Yeah, I mean, that's a very reasonable thought. I think, just give some implementations we could do. Basically, say if we have like a bunch of things that's supposed to happen at the same time, right? And then we just keep tracking of these, we make a list of them in order they're gonna be used to execute, and then, and the time that, time count, the timestamp, so to speak, where it's supposed to happen. And then, every time when the event is triggered, all the other events got updated on their timers, and then we go to do that event. And then when the next one got triggered, we update it again, and then do that interruption, do that ISR, and then just keep it tracking. This is essentially what you just said. So pretty straightforward. Obviously, there could be some issues here because you basically only works for like compare timers, and then it might result in like not so precise timing, considering the amount of timers you keep tracking. The reason, so for example, and also resulting like the slower ISR responding time. For example, if the previous event took like much longer to execute, and then the second one is already exceed the second, like the one in pipeline, then that could cause some delays. So, just give you some high-level thought, these like virtual timers could have these issues. So if you are trying to control anything that's more precise or more time critical, then trying to use like a lower level clock for that, rather than use the software clock or like a virtual clock. So these will typically be used for like, say, second or tens of like hundreds of milliseconds kind of event. But if you want to do like 1 milli, like in milliseconds or even faster, you should consider not using the virtual timer for that. Cool. So just give you like an example of what we just said, how we use the virtual timer. Basically, say we have this beautiful hardware timers, and then it keeps tracks, like the counter there is basically basically give you what's the current time, although in a different format. And then we have the program that set the timers each time before everything got executed, and then we have the ISRs list, kind of like a list to keep tracking what are the things that we need to go to, get to go handle. And we have a bunch of programs that are trying to do different things at. So for example, program 1 wants to set a timer at time 3 and 5, and program 2 wants to set at like D2, D here as a delta, as in it's a repetitive event. So every two, well, let's say time or minute, depends on unit you use, but every 2 of this counter here, time counter, that program needs to be executed one time. And program 3 have the repeated of 7, and then program 4 have repeated of 4. So basically, it goes to this programmers, and then it determines based on each of these time labels, it goes to the virtual event queue to just light them up, and then it will determine all kind of branches inside of these ISRs. Basically, each of these program handler will be pointed to a branch instruction inside of there, and then which go to the actual part where the virtual timer comes in and then handle the queues. So basically, we have the head pointer points to when this first one coming, that's going to be the first in the queue, and then have a timer as 3 here. And then we add the other event that needs to be at 5, and this timer here basically keeps track of how many count that's needed when the next event is going to happen. You can think of it as the AR values, so to speak. And just we keep adding that. We add the delta 2 to the queue, and because that is supposed to actually happen before the previous 2 events, the whole queue will be resorted so that one is at the top. And then keep adding the 7s and the 4, and then triggers another resort. So that one will go to the 3rd in the queue. And the counter basically starts, or like the program starts at this point, and every time one count passes or one cycle passes, the counter will reduce it by 1, and then everything inside of this queue will also be updated by -1. Remember the previous pipeline we have, every time when the timer updated, each of these will be updated as well. Oh, sorry. So each of them will be updated when an event is triggered, not every cycle. Sorry, my bad. So this is when the counter comes to 0, an interruption happened, which is corresponding to the first event that's going to be executed. And that's when all of them will be updated to a different value, basically minus whatever the previous value that's stored here, which is 2. So everything will be -2, and then that counter's value will also be updated, because now that we have event needs to be triggered in 1 clock, or like say 1 second in this case. And then we'll update that to 1. Does this make sense to you guys? Okay, sounds good. And then basically keep going, and then until that one go out of it's being executed, and then we update it to 1. And it could happen that the handler needs to it might occur like multiple events happen at the same time. And normally there are like a few ways to deal with these. The most straightforward way mostly is just done in like a first come, first serve, first in, first out. All these are able to be implemented based on whatever your configuration is. You can also set like a priority list, basically have like additional priority register, or just keep tracking of that, assign each of these events at like a priority level. So whenever at the same time there are multiple events are supposed to happen, you always execute the highest one. These are, I think, the 2 most common ways to handle these. There are also some other fancier ways, or like more risky ways. They also, if they are like super short instructions on the IXR and you know it, you can also just try to send them out in one batch and hope that within 1 count of the time in the virtual timer, all of these events going to be executed correctly. But for those tricks or those techniques, make sure you understand like the hardware execution down there. So, yeah. Another thing is the example we have basically assume all these events are already inside of the queue before the program starts, right? Even whenever we have like a deltas, but those are also set before this timer starts to coming down. So what if we have events that's added to the event while we executing the program? How do we deal with that with the timer or like the counter method we used? So basically, say we currently already at the hardware timer at count 1, and then we have like a time 2 of the previous examples from the program 1, 2 of the previous timers set by the program 1 in the queue, right? And then we now have a new event that's supposed to be repeated every 2 seconds added at this moment. So basically, we're gonna update the queue, but cannot wait for the next timer to expire. So we'll basically update the queue first, and then we make sure we subtract the difference from all the elements in the list. In this case, it's gonna be 2 because these events, this is supposed to happen at 3, and then the timer is already counted down to 1. So like 2 of the clock cycle, or 2 of the 2 seconds already happened in the past. So we're gonna update that number, and then, and then add, and then set it to 2 here. So that basically means the previous one is already being executed. I think, yeah. It should be an additional slice here, changing this to 0 and then switch out the order. So that one get executed first. Any questions on this? I'll update this slide, sorry. But basically, whenever you're trying to do that, make sure when you're trying to add any events to the queue, make sure you make sure you check what's the current timers at, and then subtract the amount that's already be executed along the way. Cool. That's the end of the lecture content today. And if you have any questions or if you want to check with anything with me, feel free to come down. If you want to talk about midterms after we release the score, feel free to come to my office hour tomorrow. Thank you.
No, but I will in a couple
I wonder.
Okay, so like having more than 4 is okay. That's okay.
Five would be a little bit because sometimes chances are 1 or 2. Okay, 1 and 2.
last two basically somehow.
We might have 5 hour rare cases like 1 or 5 or 1.
Okay.
4.
I had, sorry, you were trying to go ahead. My question was just about group.
I got here pretty late. Was there any way that I can still do the workshop? Thank you.
And feel free to make sure you leave at the end.
On the last slide, the last couple of slides that you went through, the hardware timer was still 1, and that one, even though the task was 3, should the hardware timer have been 3, or was it just fine to be 1 that last slide?
The hardware timer is the actual time, so that would not be changed. So basically, what we do, we will update the timer. We will update the numbers in the queue for that. So in the queue previously it was like.
It was 3.
Previously in the queue it will be updated after an event is triggered, right? But when we add in an event, so that would be changing those 2 values first, and then add the events that's scheduled at trying to add to the queue at the time, and then put that into the list to be sorted.
Yeah, but let's say the event never happened, right? How would that task be scheduled for an interrupt if the hardware timer is at 1 and the timer for the task is at 3?
What do you mean?
Okay, I'll pull up the slide right now. You can just push.
Matt told me it would be okay if I did this, but I wanted to ask you too. In my lab we have an amplifier, and I streamed it to a computer so that it outputs data values in Python and communicate with that with I2C